So we discussed the Jordan block and some very interesting properties that it has. Now what I'm going to do is I'm going to put multiple Jordan blocks together, right? So what I'm going to do is I'm going to construct a much bigger matrix, right? That is block diagonal. Okay, block diagonal meaning it's not quite diagonal, but it has got diagonal blocks. We have seen block diagonal matrices in earlier lectures also, right? And the diagonal blocks are Jordan blocks, right? So it's going to be like Jn lambda here. Okay, so I'll write Jn1 lambda 1, okay, Jn2 lambda 2, so on Jnk lambda k. Okay, so this is how I'm going to write it. So now if you look at this matrix, right, this matrix here has in the top left, it's got a Jordan block of size n1 cross n1, okay, corresponding to lambda 1, right? So if you zoom into this portion, right, what you will see is that it's actually an n1 cross n1 matrix with lambda 1s on the diagonal and 1s on the super diagonal and zeros everywhere else. Okay, that's what it's going to be. And similarly, you can zoom into each one of them. Okay, I'm stitching them all together into one giant matrix, right? So what will be the size of this overall matrix? It's going to be n1 plus n2 plus nk cross the same thing. It's going to be a square matrix of this size, correct? So I stitch them all together and this is what I will get. Okay, now why am I doing this, right? So we'll see the important result that every matrix will be written in this way, but I'll come to that later, right? Every matrix can ultimately be written like this. So remember, this is a block diagonal form, right? Symmetric matrices can always be written in terms of diagonal matrices, right? What we're going to see now is that an arbitrary matrix can be written in terms of block diagonal matrices, where each block is like this. It's a Jordan block. Okay, fine. I'll come to that later. This is just to give you some context of why I am doing this. But now let us try to understand some very interesting properties of this overall matrix. Okay, so first of all, when I write a construction like this, I don't really mandate the lambdas to be all distinct. Okay, so lambda 1, lambda k are not necessarily distinct, meaning that some of them can be same. Okay, for example, you can have a matrix like this with let's say it's a matrix of size 10 corresponding to 1, eigenvalue 1. Okay, so it's a Jordan block, 10 cross 10 Jordan block for 1, that's here, right? You could also have, let's say, 5 cross 5 Jordan block corresponding to 1 here, and you could have a 20 cross 20 Jordan block corresponding to 3 here. Okay, so what is happening in this matrix, the overall size of this matrix is 10 plus 5 plus 20. Okay, so that is 35 cross 35 matrix. Okay, and it's got these Jordan blocks. Okay, fine. So let's take this example maybe and try to investigate what are the eigenvalues of this matrix. Okay, what are the eigenvalues? In fact, what is the characteristic polynomial of this matrix? Right. First of all, you have to see that this matrix is actually an upper triangular matrix, right? If you zoom into each one of them, you get an upper triangular structure like this, upper triangular structure, another upper triangular structure, right? So this matrix is actually an upper triangular matrix. So to find the characteristic polynomial is quite simple. All you need are the diagonal entries, right? So in this case, you will get mu minus 1 whole to the 10 times mu minus 1 whole to the 5 times mu minus 3 whole to the 20. Okay, that's what you will get, is it not? Right, because here 1 is on the diagonal, so mu minus 1, there are 10 of them, right? So mu minus 1 to the 10. Similarly here 1 is on the diagonal, so mu minus 1 whole to the 5 and mu minus 3 whole to the 20. Right, if you actually do it in general also, it's very easy to write. It's just going to be mu minus lambda I to the power of ni. Okay, product of this. Okay, so these sizes, okay, in some sense are very closely related to the corresponding corresponding algebraic multiplicity. For example, so if you write this here, right, it's going to be mu minus 1 whole to the 15 times mu minus 3 to the 20, correct? So what you're seeing here is that 20 is the algebraic multiplicity of 3, right? That is basically the size of the Jordan block corresponding to 3. Okay, 15 is the multiplicity, the algebraic multiplicity corresponding to 1, and that is like the sum of the sizes of the Jordan blocks corresponding to 1. Okay, so in this matrix here, right, the first property that you will note is, right, the algebraic multiplicity of any eigenvalue is the sum of sizes of the Jordan blocks corresponding to that eigenvalue. Okay. Okay, correct? Is that clear? So it's a so that just comes from writing down the characteristic polynomial of this thing. Okay, fine. Okay, that is the algebraic multiplicity. Now what is the geometric multiplicity? In other words, what are the eigenvectors of this matrix? Okay, if we had to find out the eigenvectors of this matrix, what will they be? Well, you will not be surprised to know. Can somebody actually guess what will be the eigenvectors of this matrix? Once again, I keep forgetting it's a live lecture. So this eigenvectors, so you can see that this block, each Jordan block which we discussed in the previous part, has only one eigenvector. Okay, that will be the vector that has 1 in the first position and 0 everywhere else, right? So this block will bring with itself one eigenvector, this block will bring with itself one eigenvector, and this block will bring with itself one eigenvector. Okay, the number of eigenvectors will be equal to the number of Jordan blocks. Okay, so this matrix here will have 3 eigenvectors. Okay, we can actually write down what they are, right? The first eigenvector is going to be E1, okay, corresponding to this block over here, right? The first block. First eigenvector will be E1. The second eigenvector will be the one corresponding to this one. Okay, now for you to get an eigenvector of this, you need to have a 1 in the position where this block is beginning, right? So if you actually write down a vector, right, the first 10 positions will be taken by the first block, right? So you will have zeros in the first 10 positions. Okay, first 10 positions. At the 11th position you will have a 1, okay, and then you will have zeros everywhere else. Okay, this is going to be E11. Okay, so E11 is going to be another eigenvector. Okay, and here this block will bring in itself one eigenvector, and what will be the eigenvector corresponding to that? Well, you need to have a 1 in the position where this block begins, right? So this block begins at position number 16, right? So 10 and 5, 15 positions are taken away here. So at position number 16 this block begins, right? So you need to have E16. Okay, these are the 3 eigenvectors corresponding to this matrix. Okay, so I hope this is clear to everybody, right? If it is not clear, you can definitely, we can definitely check. So if you are in doubt, the best thing to do is just start from scratch, right? So just start with this matrix, right, and multiply it, okay, with a possible, a vector. And check for its eigenvalues. For example, if you are trying to find its eigenvectors corresponding to eigenvalue 1, so you just multiply with x1, x2, x3 and make it equal to 1 times x1, x2, x3. Okay, and you just do the math, right? So here it's a very large matrix. It's not very difficult to actually go through the steps and to see that this is what happens. Okay, I'll leave this as an exercise. This I hope should be clear from what we discussed about each of these blocks. We discussed about each of these blocks in detail, so it sort of naturally comes from that. Okay, so the main idea is each Jordan block will bring with itself one eigenvector. Okay, number of eigenvectors will be the number of blocks. Okay, so here I can also answer the question, what is the geometric multiplicity of 1? So geometric multiplicity of any eigenvalue is the number of Jordan blocks, okay, corresponding to that eigenvalue. Okay, for example, in this example that we had given, what is the geometric multiplicity of let's say 20, right? That's just going to be 1. There's only one Jordan block corresponding to 20. What is the geometric multiplicity of 1? That's going to be 2, because there are two Jordan blocks corresponding to the eigenvalue 1. Okay.